whenever you want to find the concentration of an unknown, especially if it's an acid, you can use the concentration of a known base. So you'll take advantage of one solution's concentration, which in this case would be the base. And then you use that known concentration of the base to find the unknown concentration of the acid. That's called volumetric analysis, because you're going to be using volumes and concentrations to determine the concentration of the unknown. So the process is called titration. Okay, so again, you're going to be using volumetric flasks, the burettes, pipettes, to determine the volume. And again, like I said, titration is a method to determine the unknown concentration of a substance. We call that an analyte that you're analyzing by reacting with a substance of known concentration called a titrant. So your titrant today, and this is important, your titrant today is going to be sodium hydroxide. Your analyte today is going to be the acid. The acid could be diprotic, which means it has 2 protons, for example, sulfuric acid. Or the titrant could be monoprotic, for example, HCl. Only 1 proton, like HCl, for example. So you'll use a standard concentration of your base. You will know the concentration of your base, but you don't know the concentration of your acid. So you use titration to find it. So like I said, monoprotic has 1 proton, diprotic has 2 protons, for example, sulfuric acid, carbonic acid. These are examples that you'll be tested on in the final. And then triprotic could include any acid, inorganic acid that has 3 protons, so including phosphoric acid. And then tetraprotic is going to have 4 hydrogens, 4 protons on it. It's not coming in my head right now, it's disappeared. Okay, so another example of monoprotic is nitric acid. So the way to know what type of acid you have, just look at how many hydrogens are available. There's 1 hydrogen here, there's 2 hydrogens, diprotic, there's 3 hydrogens, triprotic, there's 4 hydrogens, tetraprotic. So you need to know that, because when you write the equation of reaction, the mole ratio of reaction between the base and these acids will be different. If you're reacting sodium hydroxide and HCl, the rate of ratio will be 1:1, making 1 molecule of water. If you're reacting sodium hydroxide and sulfuric acid, then you're going to need 2 sodium hydroxides to react with 1 sulfuric acid, and so forth and so forth. So it's important to know the reacting ratio. Okay, so now, these are neutralization reactions. So if you write the net ionic equation, this is what you'll get as a net ionic. We talked about net ionic equations before. So net ionic equations, equation for neutralization reaction from our titration would be H plus with the base to give you water. And that's why I said it's very important to know whether your acid is diprotic, monoprotic, and so forth. Right now, this is assuming that the H plus is coming from monoprotic acid. If it were diprotic, then you're gonna be needing two hydrogens, 2 protons there. The reaction, the net ionic equation will be 2 H pluses plus an OH. I think should give you H2O. We'll have to find a way to balance this. Let's see. Actually, it's just gonna lead to the same one. Let me see. Let's try and do, where is it? Let's try and do an ionic equation for diprotic and see if the ratio will be the same or it's gonna be a multiple. Because it looks like it's gonna be a multiple. So let's see, sodium hydroxide, add sulfuric acid, should give you, we know it should give you sodium sulfate. Sulfate is a polyatomic anion with a charge of -2, so you're gonna get 2 down here. Sodium is group 1 element. So you drop the numbers. 2 goes below sodium, 1 goes below the sulfate. You get Na2SO4. And it's a neutralization reaction. The other product should be water, liquid. All salts of sodium of group 1 metals are soluble. We write aqueous. Obviously, this is an inorganic acid that's soluble. This is sodium salt. It's soluble. Okay, so now, balance the equation. We have to put, where do we need to put? So we'll have to put 2 here to balance the sodiums. And then now we have 2 hydrogens, 2 hydrogens. This is 4 hydrogens to your left. We need 4 hydrogens to our right. We're going to put 2 there. Okay, it's balanced. So next, let's write the ions. So you'll get 2 Na plus. Anything that's aqueous, you break it down. Anything that's liquid, gas, or solid, you don't break it down. So you have 2 protons. The acid is diprotic, you see? You have 2 protons. And then you have a sulfate. Okay, and then you have, this is in aqueous state, so you get Na plus, 2 Na pluses, you have a sulfate. And then you get H2O. Can someone tell me what should be the next step to get the net ionic? And you mute your mic and tell me. Someone?
Get rid of spectator ions.
Correct. Anything that's in aqueous state and it's in both the left and right side must be cancelled out. Those are called spectator ions. So I see I have 2 sodiums. I have a sulfate and a sulfate. So we are left with, from this equation, let me see, I'm gonna squeeze the net ionic down here. So we are left with 2OH minus, okay, plus 2H plus. Those guys will react to give you 2H2O. And that's why I was saying it's gonna be a multiple. So whenever you have more protons, you're gonna have more equivalence of water to bring up. Here we are assuming it's a monoprotic acid that was used. So you definitely just know the reacting ratio will be 1 to 1. So you get sodium chloride and H2O. So notice that the H plus will eventually react with OH minus in a 1-to-1 ratio to give you 1 mole of water, because this was monoprotic. Sulfuric acid was diprotic. That's why we have these 2 equivalents on there. Okay, so that has explained to you what should happen. Now, sometimes we use a dibasic. We can use a monoprotic acid and a dibasic base. You see, sodium hydroxide is monobasic. There's only 1 OH in the formula of sodium hydroxide. Yeah, sodium hydroxide has only 1 OH, so it's monobasic. Just like HCl is, HBI is monoprotic, sodium hydroxide, which will be monobasic. Calcium hydroxide has 2 OHs, so it's dibasic. So you can also use a monoprotic acid and a dibasic base and titrate them together, but just make sure your chemical equation of reaction is balanced to find the net ionic equation. So now let's look at an example. So this is what you might have done, because you would have taken an unknown acid, whether it would have been either H2X or HX, dibasic or monobasic. So in this case, we have a dibasic acid. So you are told that the acid that you have is of the type H2X. You're given the volume of the acid. So this is the, what do you call it? That is the analyte. This is the analyte. So your analyte will be down there on an Elmer flask. Usually you just deliver 25 ml from a pipette. Your titrant will be the base. It's going to be in the burette. Okay, this is the analyte. This is the base. So you don't know the volume. You don't know the volume of the base yet until you do titration. So that's why you have to record the initial volume of the burette. Okay, and then run in the analyte, you add an indicator. The indicator changes color whenever you have complete neutralization of the base and the acid reaction. So you record your initial volume of the burette, of the volume of the base in the burette of the titrant, and then after you get to your what we call the end point, record the final volume. If you subtract these two guys, you're going to get the volume of the base. Okay, so now, again, I repeat, the volume of the acid is known straight ahead. You don't know the concentration. You're looking for the concentration of the acid, but the volume is known straight ahead because you straight ahead just pour 25 ml of that analyte into the LMF flask. The volume of the base is not yet known until you perform your titration to find the end point where the indicator will change color in your analyte. Okay, so when you subtract this, you're gonna get the difference is gonna be the volume of the base. So at that point, you have the volume of the base. You know the concentration of the base because it's the standard, it's the titrant. The titrant's volume concentration must be known. The analyte volume, that you don't know the concentration. Okay, see, the concentration of the base is known. So the volume of the base is known, concentration of the base is known, the volume of the acid is known. You don't know the concentration of the acid. That's what you're looking for. So to calculate the concentration of the acid, the analyte, we can use the definition of molarity, which is molarity, M, is moles per volume divided by volume in liters. So it's moles per liter. Okay, that's the SI unit of molarity, moles per liter. If we can determine the number of moles of the solution, then we can divide the volume by, the volume, which is 25 ml of the acid, and then we'll find the molarity. So too much information there, but also what you want to know is that the reacting ratio is 1 to 2. Why 1 to 2? Because it's a diprotic acid. Okay, so again, I'm gonna write the equation here so you'll see what I mean. You have H2X reacting with the monobasic base, sodium hydroxide. The X could be a sulfate, could be a carbonate, could be anything. So what we know is that the sodium, you get NaX, and you're gonna get H2O. Now remember here, the hydrogen has a charge of +1, which means the anion X will have a charge of -2. Because if you drop the 2, you get H2X. You drop the 1, you get H2X1. So in this case, the valency here for sodium should be 2. Why? You are exchanging the charge of the anion with the charge, the absolute value of the charge of sodium. So drop that number, drop this number, you get Na2X. That's how I knew this is the formula of Na of sodium X, the salt. So next you have to balance. So 2 comes here, and then 2 will go there. Now look at the balanced equation. For 1 mole of the acid, you're reacting with 2 moles of the base. So the reacting ratio is 1 to 2. Why is that important? It's very, very important because if you use the formula of finding moles of the base reacted, if you find 2 moles of the base here, then it means that you reacted it with 1 mole of the acid. If the moles of the base that reacted was 10 moles, then the moles of the acid that reacted was 5 moles. The reacting ratio is 1 to 2. Okay, so now we'll get back to the equation shortly. So the volume of the base that was used comes from the subtraction of the initial and the final volume of the base. So it turns out to be 31.56. The moles of the base that was used can be found using this same formula. If molarity is moles over volume, then it's obvious that moles can be found by multiplying the concentration, the molarity, by the volume. So that's what's being used here as the formula. Turns out that the concentration of the titrant is known. It's a standard, is 0.1186. Multiply that by the volume of the base. You realize that when you subtract the volume, you get 31.56 ml. But our formula has the volume in liters. So you really have to convert the 31.16 from ml to liters. To do so, you divide by 1,000 because 1,000 ml makes 1 liter. Okay, so you do this math. The volume of the base that was used from the burette will turn out to be 0.03156 liters. So now we use that volume here. We are trying to find the moles of the base. So multiply the concentration of the base that's given to you, that's known. It's a titrant. You always know the volume of the concentration of the titrant. Molarity times volume. So you realize that the units for the molarity is moles per liter. The volume is liter. So check out the SI units. They're canceling out. So the L and L goes away. You're left with moles. So the answer should be moles of the base. Turns out that's the moles of the base. Now, if this is the moles of the base, what will be the moles of the acid? You go back to the reacting ratio. All right. So if these moles belong to the base, so the moles of the acid will be half the amount because the reacting ratio is 1 to 2. For each 2 moles of sodium hydroxide, you get 1 mole of the acid because it's diprotic. It's not 1 to 1, it's 1 to 2. So to get the moles of the acid is very simple. Take the moles of the base, multiply by a half, or multiply by the conversion factor. For every 1 mole of H2X, you react 2 moles of sodium hydroxide. So make sure the moles of sodium hydroxide is the denominator, so the units will cancel out, and then the answer that you get will be in terms of moles of H2X. And you see it's very correct because 1.872 times 2 gives you 3.743, which goes with the reacting ratio 1 to 2. Now, I'm going to ask you a question. Someone unmute your mic. What if this acid was HX? What would be the moles of the acid? Again, I ask the question, if the acid version that was reacted was HX, what would be the moles of the acid? Given that the moles of sodium hydroxide is 3.742 times 10 to the power minus 3. Someone? Is that a tough question? Let me write the equation of reaction. So assume you had HX reacting with sodium hydroxide. You're gonna get, okay, again, now looking at here, I know hydrogen always has a charge of +1 and it's neutral, so which means the X must be having a charge of minus. If I'm exchanging the anions with the reactant, so I expect to get NaX, right? Because sodium has a charge of +1. So they have the same absolute numbers of 1 and 1. If you drop the 1s, you get NaX. And then you get H2O. So my question is very simple. If the moles of the sodium hydroxide reacted is 3.743 times 10 to the power minus 3 moles, what moles of HX reacted? Unmute your mic and tell me. Okay, let me ask it now in a different way. What is the reacting ratio of HX and sodium hydroxide? Someone?
1:1.
Okay, it's 1:1. So what would be the moles of HX? It's just gonna be the same one, right? For every 1 mole of HX, you react 1 mole of sodium hydroxide. So if you're given 3.743 times 10 to the power negative 3 moles, it's gonna be the same moles of HX that reacted. Because the reacting ratio is 10 to the power, the reacting ratio is 1:1. So the answer would be 3.743 times 10 to the power 3 moles of HX. In this case up here, reacting ratio is 1:2. So if you have 3.743 times 10 to the power minus 3 moles of sodium hydroxide, you're gonna have half the amount on the moles of the acid. And that's why we multiplied it by half, because the reacting ratio is 1:2. Okay, do you have a question on that part, someone? All right, so you remember we are looking for the concentration of the acid, the analyte. We don't know the concentration of the acid. We don't. So we first determine the moles that reacted. But now what we do know is the volume of the acid that was used. The volume of the acid was 25 ml. Now we just determine the moles of the acid that reacted. You go back to this equation right here. Molarity is moles per liter. Given that now we know the moles, we already know the volume, we can find the moles of the acid, the molarity of the acid. So we take molarity concentration is moles per liter. So it's going to be 1.872 times 10 to the power minus 3, which is what we found right here. Divided by the volume. The volume must be in liters. Here it says 25 ml. So it's going to be 0.025 liters. Divided by 0.025 liters. The answer you are looking for is 0.07486 molar concentration of H2X. And that will be the goal of the lab, to find the concentration of the analyte, in which case it's the acid. Someone has a question? I'm giving you 3 seconds to unmute and ask before I switch gears here. No question. Now, I mentioned something called the endpoint. That's an indicator that you use. So during titration, because the sodium hydroxide and the acid are colorless, there's no telling when you have the equal ratio of reaction, when you've just neutralized your base or the acid. So to detect the endpoint of neutralization reaction, we use indicators. They're called indicators because they indicate when your neutralization is done. Okay, so indicators change color under different circumstances. So it depends on the type of indicator you're using. It could change yellow, red, blue, from blue to colorless, pink to colorless, colorless to pink. It just depends. So you want the endpoint. The endpoint is evidenced by the indicator when there's going to be a visual color change. So you want to get to your endpoint, which is a place which is as close to the equivalence point as possible. What is the equivalence point? The equivalence point is when you just neutralize all the acid has just been neutralized. There's no excess. That's the equivalence point. The end point is the point where you know it's done, it's finished. Neutralization is over. So whenever you're doing your titration, you start this way, and then you have your base on the in the burette, you have your acid in the flask. Sometimes it's usually reversed, but we usually like putting the base in the burette, the acid in the flask. So remember, based on the difference on the initial and the final volume, you can find the volume of the base. You already know the concentration of the base. So MV is known, can be found. But here, the only thing you know is the volume of the acid, VA. You don't know MA. That needs to be found. So if you know MB, the concentration of the base, and the volume of the base, one can find the moles. Based on the reacting ratio in equation of reaction, balanced equation of reaction, you can determine the moles of the acid that reacted. Knowing the moles of the acid, volume of the acid, you get to know to calculate the molarity of the acid, and that's the process. So anyway, you have your base in the burette, you have the acid in the LMR flask. You put the indicator, you see it's dropped into the acid. You put your indicator in the acid. So in this case, it's gonna be, the indicator is gonna be phenolphthalein. The color of phenolphthalein in acidic medium is colorless, like it's clear. The color of phenolphthalein in basic medium is gonna be pinkish. That's why if you keep on adding the base and go too far, the solution maintains its pink color. You wouldn't have wanted to go that far. You only wanted to go where there's a very faint pink color that stays. So you add your base. When you add your base, as the drop of the base drops in the acid, the pink color will appear, but it's going to disappear because you have excess of the acid in your flask. So you keep slowly adding the drops until the point where if you shake the Elmer flask and the pink color persists, the faint pink color persists, then you know, hey, I'm almost going to add an extra drop. I don't want to do that. So you stop there. That will be your endpoint. If it's a definite, very deep pink color, you've gone too far. And I sent the 2 version, I think, of the video, and you can see those ladies explaining that you don't want to go too far. You want to stop where it's just faintly pink for phenolphthalein. So usually at the end point, the color will persist for 30 seconds, and then it's gonna disappear. That's how you know you are at the end point. If you add an extra drop, into this, an extra drop of the base, it's gonna take you there, which means you've added too much base. You want to stop at the point where just the acid, at the point where just enough of the base has been used to neutralize the acid. You don't want to go and have an extra excess of the base in the solution. That's termed as the end point. Okay, the closer you get to the end point, the longer the color will stay. The closer you get to the end point, the longer the color will stay. But you'll still need to do slow addition of the titrant, which is your base, to avoid overshooting. So overshooting means adding too much of the titrant, too much of the base from the burette. So when the pink color first shows, you should cease a constant addition and only add about 0.5 millimeter at a time. This would have been how to determine if you're approaching the end point. But I would have said that if you really want to be accurate, when the color takes long to disappear into solution, you are at your endpoint, you should stop. As you get closer to the endpoint, you should taper off the addition to dropwise until you reach the endpoint, correct? You don't want to keep running the solution randomly when the color is taking long to disappear. So now, all this is the procedure that you would have followed. There's a YouTube there, a link. But let me play an animation for you. So I'm going to repeat myself in this PowerPoint. I'll add it later on the Moodle page. So you take your unknown, which is gonna be the analyte. And in fact, for you guys, your analyte is gonna be either H2X or HX. I'll tell you which one you should use. Okay. So you have 25 ml of unknown analyte. You add it to your LMF flask. So use a pipette and add it to your LMF flask. All right. So that's the 25 ml, 25 ml of acid. Like I said, depends on what you're given. So let's say you have H2X or you have HX. We don't know the concentration. You're looking for the concentration. So that in there, we're gonna add the indicator. Our indicator is phenolphthalein. Remember, phenolphthalein is clear in acidic medium. You're gonna be tested on this. Clear in acidic medium, but whenever you are doing a titration, you get to your endpoint, it's gonna be pink in basic medium. That's how you'll know you reached your endpoint. And that's why it's called an indicator. It tells you when you've reached complete neutralization. It indicates when you reach complete neutralization. So you have your acid in here. Remember, it was 25 ml. Okay. You add your indicator into the acid. It does not change the color of the acid. The acid should stay clear. I'm just using the color here, blue color, just to know that you have a volume of liquid, but it just be the color of water. So you added your indicator. Added your indicator, usually like 3 drops, like that. And then you do your titration. You need to record, sodium hydroxide is in your burette. You would have needed to record the volume of your sodium hydroxide, the initial volume, we call it VI. So suppose this is our VI. After titration, that's our VI, 1.26. I hope you know how to read. This is 1.1. This is 1.2. It's roughly below the 0.5, so we take 1.26. 1.2 for sure, we guess the 6. So that's your VI. V initial. Others called VI. So we don't know how much of the base will be used. That is going to be determined by the endpoint. So you titrate, dropwise, 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 dropwise. You get your endpoint where the color is faintly pink. Remember, if you add 1 extra drop, it's gonna go here. You don't want that. This is too far. Okay, so this is the good endpoint. That's an accurate endpoint. So you don't know what volume of sodium hydroxide was used. So at this point, you want to read your volume again. So our volume here, this is 20, this is 20, this is 20.1, This is 20.2. Okay, now it's roughly 20.25. So this one, this volume now is not going to be called V initial. It's going to be called V final, because it's after you titrated. So this will be a V final. Okay, let me see if I can use my pen one more time. So this will be a V final. What's the time? Okay. So V final. So to find the volume of the titrant, remember that's your titrant. It's the titrant has a known concentration. Known concentration. This is your analyte, the acid. The analyte is the acid. So you titrate the analyte with the titrant to the end point. The color changes pink. You get a difference in volume of your titrant, and that gives you the volume of the base used. So in this case, the volume of base used, which is the base is sodium hydroxide, is going to be equal to VF minus VI. So in our case, it's going to be our final volume is 20.25. Initially, I think it was 1.26. The answer is going to be in mLs. Okay, so you would subtract that. So that's what exactly that's done here. I think, let me clean up. I wanted to circle the right point. Let's see. Okay, so this was your VF. This is your VI. Do the subtraction. It should give you 18.99 VF minus VI. So that would be a rough one, but you can do trial 1, trial 2, time 3, and get numbers in there. Of course, this is the concentration of the base because it's known. If your reaction is H2X, then the base acid to base ratio will be 1 to 2, 1 to 2, 1 to 2. Moles of sodium hydroxide. How do you determine moles of sodium hydroxide? Someone unmute and tell me. I walked you through that. Someone tell me. Moles equals to molarity times volume. So we know the molarity is you're given 0.4 molar. So in this case, it will be 0.4 moles per liter. That's what the uppercase letter means. Multiply that by the volume. So the volume in this case is 18.99. So in liters, it's 18.01899 liters. So L and L will cancel. I'm trying to do this part right here. Let's see. Actually, that will be the part that will go in here. And L will cancel, then you get, okay, so 0.4 times 0.01899. I'm getting 0. Someone saying something? Okay, 96 moles. You really don't need to fill up where it's blanked. I'm just using this as an example. So again, to find the moles of sodium hydroxide, I multiplied the concentration by all these volumes that you'll be getting in these boxes. That's how you're gonna get the moles in these boxes. So I'm just using the first rough to determine. So if this is the moles of sodium hydroxide, what is the moles of the acid? So you will take, so you remember the reacting ratio is 1 to 2. If for every 2 portions of the base, you get 1 portion of the acid, which means the moles of the acid here, because we are using H2X, will be half that. So I'll do the moles of the base divided by 2. So the moles of the acid, I think, where is it? It's not here. I will need to include that table. The moles of the acid, let me write it out here. The moles of the acid is 0.007596 moles of the base divided by 2. Because the reacting ratio is 1 to 2, the moles of the acid turns out to be 0.03798. So how do I get the concentration of the acid? The concentration will be molarity equals to moles per liter. I just did the moles of the acid right here. So I'll use those moles and say it's going to be 0.003798. Okay. And then I'm going to divide it by 2, not divided by 2, divided by the volume of the acid that was used. It's here. The volume of the acid that was used is 25. This 25 is equivalent to 0.025 liters. We always work with liters in the formula. So I'll divide this by 0.025 liters. So you have moles on top. You have liters at the bottom. So you get moles per liter, which is the definition for molarity. So I'm going to divide my answer that I got there by 0.025. Turns out the concentration right here is 0.152. So you do the same for trial 1, do the same for trial 2, do the same for trial 3. Okay, and then you can find the average. Yes?
Are we using H2X? Like, are these the numbers we should be using for our report?
No, I'll give you the numbers. This is just an example. This is just an example. So from there, you can find the standard deviation. You know, you have your average. You can always find your standard deviation and find the percentage RSD. We did that face-to-face instructions. So you can do that part. Okay, so let's see. So I'm going to go now to the report. And the next few minutes, let's see. So I'll give you this part. In fact, let me show you what I mean by after the class, maybe somewhere 2 p.m. I'll give you the numbers, and all I need you to do is to fill up. It's just to fill up the chart. Okay, let's see. Actually, it's very, very straightforward, just like I've explained. Oh, where is my file? Did I lose my file? Let's go sideways and see. Oh, there it is. Okay, so this is an example of what you will do. Actually, if you continue filling up the numbers, these are the numbers that you should see. So I'll give you the numbers. I'll load the report, and the report is gonna have its numbers. So you'll have to fill it up, okay? And then let's see. I'll put one of these as an example. So if you want to practice to make sure that you're doing the right thing when you do the calculations, the answer should fall in place. So that's what you'll do. So you'll be given these numbers on the first rows, 1, 2, 3. Okay. the row number one, volume of the acid, initial volume, final volume. That's the information be given. I'm going to insist that you're gonna check the value of H2X. Okay, and I'll give you both. I'll give you H2X and HX, so you know how to do it, both of them, because one of them might show up in the final, and I really want to make sure that you know how to do it. Okay, so now let me go to the report. Where's my report? Here's the report. Okay, so this is what you will see for your report. How do I type in? Okay. I want to get out from the pen, but it's not letting me. Okay, so let's suppose here your initial is 0.5. Okay. And these are the make-believe numbers that I'll put on your reports. And then, like I said, I'm gonna put two tables, one for here, I'll put one for HX, and I'll put another one for H2X. The calculations that you'll show is gonna be the calculation for the one that is for H2X only. But both tables must be filled up correctly. So the final volume here, I'll probably say 34. You know, these are just arbitrary numbers. So let's say again you started at 0.50, and then you got, let's say, 33.75. You started at 0.50. Well, it's not 3. Let's say this is 34.20. You started again your initial at 0. Maybe you started this time at 0.07, 0.70, sorry, and your final turned out to be 34.30. So to find the volume here, okay, let me bring back the pen. And this is just an example, by the way. So this is your VI, this is VF. So this box here would be VF minus VI. All these boxes would be VF minus VI. The concentration here will be given. So probably you'll be told the concentration, let me see. This concentration must be given because it's a titrant. So let's say this is 0.215 molar. So once you get the volumes of the base, multiply by the molarity, volume multiplied by, moles equals to, moles, what did we say moles equals to? We said molarity is moles per liter per volume, okay? So which means moles will be equal to molarity times volume. That's what you'll need to do here. To find the moles of the base, it's gonna be M times V. Just make sure that your volume is in liters. Okay, molarity times V in liters. Molarity times V in liters. So whatever volume you get here, it's in mLs. You'll want to use the liter version of whatever you get in up all those boxes. And the concentration is constant for the base. It's simply what you're given. It's a standard. And then if it's HX, you'll know that the reacting ratio is 1:1. You want to balance the equation if it's HX. If it's H2X, the reacting ratio will be 1:2, like I did in the PowerPoint. Okay. Then if it's 1:1, whichever moles you found here is gonna be the moles of the acid. I'm gonna create an extra table here. Okay. I'll create an extra row that's gonna read moles of acid. Okay. In fact, let me try and do it right now, so you'll get an idea of what I mean. Yeah, so right here, I'll have you tell me the moles of acid. So based on the reacting ratio, you should know the moles of the acid. If it's 1:1, then it's the same. Whatever moles you found here will be the moles here, if it's 1:1. If it's 1:2, then you have to divide the moles of the base by 2. Then from there, to find the concentration of the acid, you will take the moles that you will have found on the previous row and then divide by the volume of the acid in liters. Remember, the volume of the acid is 25 ml. You see up here, volume of the acid is 25 ml. So that's the volume that you'll use down here. But just make sure it's in liters. Make sure it's in liters. That's how you'll get the molarity of the acid. And then, of course, from there, you find the average and then do the standard deviation thing. Down here, breakdown on how you'll show your maths. And like I said, I'll need the calculation only for the H2X table. Okay, only for the H2X table is what I want you to show. Here, to answer these questions, you just have to write the equation of reactions. I'm guiding you on how to do it. Write the equation of reaction. In fact, it should be balanced. If you're not sure about the formula of hydrochloric acid, calcium hydroxide, you can Google that. If not, you know calcium is in group 2. Hydroxide has a charge of -1, is a polyatomic anion. These absolute numbers drop. So the formula should be CaOH2 for calcium hydroxide. Potassium hydroxide, of course, is charge of +1 and -1 is just KOH. Magnesium hydroxide, magnesium is in group 2, like calcium hydroxide, so that should be the formula of magnesium hydroxide. Sodium acetate. Acetate is CH3COO minus. It has a charge of -1. Sodium has a charge of +1. So the formula for sodium acetate is NaCH3COO. You can write it like that. Still okay. Okay, so citric acid, you can Google the formula of citric acid. You can Google, you can find the sodium of sodium hydroxide. Write the equation of reaction. That's what I'm looking for. Once you write the equation of reaction, find the molar ratios. That's what you need to post here. Very, very straightforward to do. Phosphoric acid is H3O plus, H3PO4. I mean, it's H3PO4. So it's H3 plus PO4 3 minus, sorry. That's the formula for phosphoric acid, H3PO4. Again, just add this together, do the reaction ratio, you get potassium phosphate and water, find the molar ratios, post them on there. I think what's left is just general questions. So that's how you're gonna do your report. Like I said, I'll modify the report to have 2 tables, and the only calculation that need to be shown is only for H2X. All right, do you have any question before I end it?
Can you repeat how we would go about finding the moles of acid?
Okay.
That new one you created?
All right, so do you know how to find the moles of the base? Let's start there.
No.
Okay, do you know how to find the volume of the base?
No.
Okay, so the base is in the burette, right? So we said you have to record the initial volume before you start. Remember?
Yes.
And then after you titrate, the volume is going to be down here. You're going to get a final volume of the base. So the difference will be the volume of the base. Now, is that clear?
Yes.
And that goes on this row. It's going to be in ml. the concentration of the base is given straight ahead. It's given ahead of time because the base is the titrant. The titrant always has known concentration. All right, so to find the moles, it's gonna be the molarity, which is 0.215, for example. I'm just using these numbers as an example. Multiplied by the volume. The volume is right here. This volume is what you got in these rows. Like that volume will be what found there. This volume will be what you found here. This volume will be what you found here. So to find the moles, it's moles times volume. So moles equals to concentration times volume. Molarity times volume, sorry. Moles is molarity times volume. That's why I wrote the equation there. Are we okay to that point?
Yes.
So that's the moles of the base. So how will you find the moles of the acid? You have to use the equation of reaction. If it's HX, then the reacting ratio is 1:1. Let me see if I can write here. So if you are reacting sodium hydroxide and HX, then you're gonna get sodium X and water. Remember what we said in the manual? The reacting ratio is 1:1. So if arbitrarily, if the moles of sodium hydroxide, in fact, if I use my example here, if I multiply 0.215, which is the molarity, times the volume here, which is the difference, times, what's the difference there? 34 minus 0.5, I'm dividing it by 1,000. I'm getting the moles for this place to be 0.0072. So if that's the moles of the base, if this is 0.0072, tell me what's the moles of the acid? Can you tell me? Remember, the reacting ratio is 1:1. For every 1 mole of sodium hydroxide, you react 1 mole of HX. What's the moles of HX? I'm waiting, you have to tell me. Or someone out there, can you tell me what will be the moles of HX if she can't get it?
Wouldn't the moles be 1:1 ratio as well?
It's 1:1 ratio, so I want the number of moles here. We just found the calculation of moles of the box here is 0.072.
Oh, so then it would be the same too.
Yeah, it's the same. The reacting ratio is 1:1. Now, if this was H2X, it would be a different story. So if sodium hydroxide is reacting with H2X, then you're gonna get Na2X, because obviously then it means this X here, the anion, has a charge of 2- plus water. Now you have to balance it. So we put 2 there, we put 2 here. Now the reacting ratio is for every mole of the acid, you use 2 moles of sodium hydroxide. So what would have been the moles of HX? Someone tell me. If the ratio is 1:2, acid to base, what would be the moles of the, what would be the moles of the H2X? If we were using H2X and not HX, what would be the moles of this guy down here? If here we have 0.0072. Someone? What will you do?
Would you divide by 2?
Yeah, you just divide by 2 because the reaction ratio is 1:2. Now you really have to get this because, and again, I'm recording it. I'll post this video lecture on Moodle so you can replay it over and over again if you get lost. So anyway, here the reaction ratio is 1:1. So it's gonna be the same moles here. Now you need the concentration of the acid. We still do the same thing. The concentration, we use the similar formula. The concentration of the acid will be found by this formula. So we already know the moles. So we'll take 0.0072. I'm writing in the table, so it's not letting me write. 0.0072 moles of the acid. Divide by the volume. What's the volume of the acid? This guy, 25 ml. That's what you had in your Amel flask. So the 25 ml must be used in liters. So you divide by 1,000. It's going to be 0.025 liters. So that's how you'll get the moles. That's how you get the moles of the base, get the moles of the acid based on reacting ratio, 1:1, and then use the moles of the acid divided by the volume of the acid in liters, you get the molarity of the acid. Did that answer your question, whoever asked?
Yes, thank you.
Is there any further question? All right, so remember that this is arbitrary numbers. I'm gonna post the numbers in your report, and then you'll have two tables for HX and H2X, okay? And then just give me the numbers that are in there. You know how to find standard deviation from the earlier experiments and the percentage RSD, and then only show the calculations for H2X in the calculation part. All right, so let's end there. And please remember again, last reminder, if you've not sent me the report 5, send me an email so I'll give you one more chance to upload your report. Okay.